Yes, sir.
Yes.
Yeah, we are ready. Yeah, can I start?
Okay.
Good evening, everyone. Okay. Yes, shall we start?
No,
Yeah,
please
yeah.
go ahead.
So let's start today's webinar. Good evening, everyone. I Kanak Raj on the behalf of Data Science Society. We are going to start our today's session. I have joined with my colleague Rohit Singh. Today we have two prestigious guests with us. Uh, First one is Dr. Viral Shah, sir. He is co-founder and CEO of Julia Computing, and another one is Dhairya Gandhi, sir, who is author of Julia Plus Library. Dr. Viral Shah, sir, has been the recipient of Wilkinson Prize, and from India itself, and he is currently CEO of Julia Computing, and he was also man behind the policies and technology of Aadhaar-based systems for the government payments and the e-KYC platform. And Mr. Dhairya Gandhi sir has been from BITS Pilani. He is currently at Julia Programming, and he has been developing the Julia machine learning and differential programming ecosystem for a long time. And now, sir will start with the basic of Julia computing.
Okay. Hi, everyone. This is Viral Shah. Even though on the bottom we have Dhairya Gandhi, it's Viral and Dhairya giving this talk. And the plan is that I will speak for the introductory parts about Julia, the project, and how we got here. And we can have a little bit of sort of questions. Either put them in the chat, and the moderators will read them out, or I don't know what the process is. And then Dhairya will sort of talk about. Dhairya is the author of the Flux ecosystem in Julia, all of the deep learning, and then he will walk you guys through some of what we're doing on deep learning and scientific machine learning as we go along. So without further ado, here we are. So why Julia, right? Yeah, that is, why does someone start and create a new programming language, and what's the purpose of it, right? So we started Julia in about 2009. It's been almost 11 years that we've been working on it. And the last 25 years, we've seen, not even 25, I would say in the last 50 years, we've seen sort of languages like Python, R, SAS, and MATLAB, right? So you have languages that are easy to work with, where you don't have static typing, where you have an interactive REPL, you can do interactive plotting, you can work with your data sets, load them, explore them interactively, and sort of stay at the algorithmic level when you're trying to work with solve the problem that you're trying to solve. And it is these languages that often people prefer to use, and I'm sure many of you are using the same languages when you are working with new algorithms. But then when you need to write these programs for production purposes, to put them on servers or to run them at higher performance, often what ends up happening is that people end up rewriting the core computational kernels or the entire programs themselves into C++ or C# or Java or one of these kinds of languages. And this is what is called the two-language problem, right? That you end up using one language for productivity and another language for performance. And what Julia really wants you to be able to do is, the reason why we started Julia, right, is that we wanted to combine these two things, right? So we wanted the ease of Python and the speed of C all in one single platform, so that you don't have to rewrite your program when you end up deploying it. You don't have to rewrite it for performance. You don't have to rewrite it for a supercomputer, or you don't have to rewrite it when you put on an embedded device, because let's say something like Python might be too slow because of its interpreted nature. And so this is how the Julia language was started. And when we started this project, it was not obvious that you could have ease of use and performance in a single language. It was always believed that it was almost believed to be almost like a law of physics that you needed two languages and that some were easy to use and some would be fast. But the fact that you could have both of them in a single language was sort of the hard problem that we set out to solve. And we've been very lucky in our journey. Actually, I wanted to, just give me a second here. I was trying to pull up a slide which is hidden. How do I unhide this slide? Dhairya, would you know how to unhide this slide?
Yeah, just uncheck the just right click on the slide and click on skip slide again. Yeah. Up a little. Yeah. Down. Yeah.
I see. Got it. Thank you. So this is a little bit of the history of the project. Like I said, we started out in 2009. There were 4 of us, actually. I was one of the original co-creators, and my role was to bring a lot of the team together and then focus on what became the mathematic and scientific parts of the Julia language. Of course, we had Alan Edelman, who is the person, Professor Alan Edelman, who hosts the Julia lab at MIT. And then my colleagues, Dr. Jeff Bezancel and Stefan Krapinski. Jeff has been the original language designer and compiler writer for the project, and Stefan also worked, with me and Jeff on language design and many of the runtime parts of the system. So this is how the team sort of came together, and we spanned a number of different capabilities, right? So we have people like Jeff who are sort of at the language end, or people like Stefan who are sort of working on data science at Etsy. When the project started, I came from a background in technical and scientific computing, and then Alan, of course, is one of the pure mathematicians amongst the mix. And so we started out in 2009 with the discussion around a new language. It just literally started around as an email thread between the 4 of us, and in 2 days we had the first lines of code and a working Julia parser that Jeff put together, and it kickstarted the project. In 2012, we actually announced the project, and it went live. It became a well-known open source project. We announced it on Hacker News and Reddit, and it literally sort of caught on all over the internet. And we got a ton of contributions in that first year in 2012. In 2013, we ended up, Julia became the JU in Jupyter. Julia was the second language added to Jupyter. Back then, it was still called IPython Notebook. So with all of that, in 2015, we saw some of the early desire for having commercial support, that there were companies that wanted commercial support for the language. And that's when, the 4 of us founded Julia Computing. We quickly hit the first 1 million downloads, Julia 1.0 in 2018. 2019 saw us receive a couple of prizes, the Wilkinson Prize and the Sidney Fernbach Prize. 10 million downloads, and today we are at 25 million downloads, and we are just about to release Julia 1.6 in the next week or so. The next month or so. So it's been a long journey, and this is, for those of you who are still young in college and, at the early parts of your career, still trying to figure out what it is that you might work on, what it is that, you may want to do with your life, right? This is not easy, right? We have been working at this for over 11 years. When I started the project, I was actually working for the government of India on the Aadhaar project, and Julia was what I worked on at night and on weekends. And it was several years before, when we started the company, that I could actually work on Julia full time. And the same was true of Jeff and Stefan as well. Jeff was writing a PhD. Stefan was working at Etsy. And we just sort of had to work for years before we even ourselves knew that this is going to go somewhere. But we've been very fortunate that the community really took this on, and we've received the Julia project on GitHub, for example, has over 1,000 contributors to the project, 1,000 contributors, and that's just a mind-boggling number, like that you cannot imagine when you start something like this. But I'd love to re-emphasize the key message that you have to stick with something that you care about, that you're passionate about, and then put in that hard work and put in, those 10 years. And we are barely just getting started at this point. There's over 10,000 companies using Julia out there in some form or shape that we know of. Some of the best Fortune 500 companies are using Julia. Some of the best startups are using Julia. We're working with several startups in India as well that are using Julia today. So it's just really amazing to see how a project that I started while I was in India, a project that has a ton of Indian open source contributions, probably one of the few major open source projects with a significant component of contributions from India. It's just fantastic to see it sort of take off in such a big way. We've seen over 1,500 universities that are using and teaching Julia. Unfortunately, Indian universities are a bit lagging behind on teaching Julia, but some of the best universities are already using and teaching Julia itself. We have seen Julia being taught at a few of the Indian colleges, in a couple of IITs, in a couple of, at IIIT Delhi. But by and large, because our education system is centrally driven and the curriculum is centrally set, we need to be able to sort of, incorporate Julia in the right places before it is taught in India in a big way. But students, on the other hand, are some of the biggest contributors to Julia. And the Google Summer of Code is where we get a lot of our contributors from every year, especially usually at least half of the Google Summer of Code participants that are selected on a very strict merit-oriented process are actually from Indian universities. And these are students who are learning Julia in their spare time, working with other colleagues and seniors who have been through GSOC and really sort of joining the community early on before they make their GSOC application. And it's amazing to see this level of commitment from students in India, as part of an open source project. And many of them have gone to not just do one GSOC, but several GSOCs, work with us on Julia Summer of Code, present at JuliaCon, go to conferences, write papers. And some of them are now working at Julia Computing, others are pursuing PhD. So it's just fantastic to sort of see such an engagement, especially from colleges, in India itself. And this is something where I would encourage and urge everyone that even, the reason I say all of this is that you do not necessarily need to work on Julia or science, even though I personally think that science is the way to solve all of the problems that face the world, and computing is one of the three pillars of science after theory and experiment, right? That's my view of the world, and many of us who work on the project here share the same views. But as a young person in college, what you may want to consider is, get those GitHub commits going, whether it's Julia, whether it's another open source project that you care about, but get yourself out there, make contributions that are visible on your CV, right? Your new CV is not LinkedIn, it is not the resume, it is your GitHub profile. So Julia has seen rapid adoption for a young language. There was a very nice article about how Julia is the basis of all climate science codes in the Christian Science Monitor, one of the major mainstream newspapers worldwide, and that just happened 3 weeks ago. I would urge you all to sort of read about how Julia is reshaping climate simulation. So with all of this, Julia has risen up to, the top 20 on IEEE Spectrum language rankings. It's been covered in all the top magazines, journals, so on and so forth. So, let's talk a little bit about the technology behind Julia, right? Why does it matter at the end of the day, right? And here are some comparisons with Python. And usually I used to show comparisons of Julia, benchmarks of Julia that I had written back in the day. But increasingly now there are other people who write these benchmarks, and it's just fantastic for us to show them. So here's the computer language benchmarks game where Julia is 30x faster. This is, the language benchmarks game. It has been a very long ongoing project that has been sort of housed within Debian, but I don't know if it's truly actually a Debian project itself. But it's the same same programs that are implemented in a number of different languages. And you can see here that Julia is right here with C and Fortran and Rust in terms of performance, and you don't see any of the interpreted languages on this page. They actually go on to the next page. If you compare with graph processing in Python, Julia is 100x faster. If you compare with scikit-learn, the Julia k-means, there is a parallel k-means package that's 100x faster. H2O.ai is another company out there that produces benchmarks of data frames, and Julia turns out to do incredibly well compared to pandas and R on data frames, for example. And then here's our good old friend CSV loading, right? Just loading data from files. And the Julia CSV parser is written completely in Julia itself, and it's fully multi-threaded, and it often tends to read files significantly faster than other languages, just because it's just so easy for Julia programmers to leverage parallel computing, whether it's at the instruction level, or it's at the multi-threading level, or it's across distributed nodes. Now here's what oops, there we go. Is this going to play? Don't think it wants to play here. Okay.
Yeah.
Anyways, this was supposed to be an animated GIF, but I think it's having a little bit of a problem here. But Pluto is one of the really nice notebooks in the Julia language. Jupyter was the original one, but now we have Pluto, which has which is reactive and lightweight and simple. It's been created by Fons out of Amsterdam, Fons Vanderplas, and Fons has an amazing vision for what interactive computing with Julia should look like. And think of Pluto notebooks as being something like Excel, right? So when you change one cell, all the dependent cells will automatically change, and this is what Pluto sort of achieves. It's an amazing system. I would urge you to check it out. There is also a class, computationalthinking.mit.edu, which is a completely open Julia class. Anyone can take it. It was taught last semester at MIT. I received over 100,000 views for every video on YouTube. So if you're keen on learning Julia and Pluto, I would urge you to go to the computational thinking class at MIT. I think at this point I will pause because GPUs are part of the machine learning part of the talk, where I think we'll have Dhairya sort of take off from me and talk. So I'm just wondering if there are any questions from the audience or anything I can engage with before I sort of take leave.
Yes, sir. We have a question from Akshay Dubey. He is asking, what is the estimated time for Julia to take over Python?
I don't have such an estimate, and that is also not the goal, by the way. The goal is to continue building the best open source ecosystem. It's not a race, right? It's not a foot race where you have to sort of beat the other guy. It's not a zero-sum game, right? So often when we go to college, we think of zero-sum games, right? That for me to get ahead, someone has to get behind. But in the real world, the real world is not a zero-sum game, right? So Julia and Python can both grow, will continue growing, and have different purposes and reasons for existence. Where can we learn Julia from, right? So I would say go to the julialang.org website. You'll see tons of materials there. The computational thinking class at MIT is a phenomenal class. So if you go to computationalthinking.mit.edu, and maybe Dhairya can even load the the class website.
Rishika is asking, can the compiler itself generate code with high performance in Julia?
Yes, that's exactly what happens. The Julia compiler is what generates all the, so why is Julia fast, right? At the end of the day, the reason why it's fast is because you have, Julia actually generates native assembly code, and that's what really, really makes it fast. So there we go. Oh, that's the computational thinking class. Yeah. So if you look for some of my other talks online, I actually show why Julia is fast, right? If you just go to YouTube and maybe plug in my name, you'll see, what makes Julia fast. And it basically is, because it generates native assembly code and executes that as opposed to interpreting it. And why then comes the question of why is Julia fast and why is Python not fast? And but I would probably not want to answer that right away because we are going to not have enough time. But there are several of my talks on YouTube and several other amazing Julia talks on YouTube that you should check out. I would also urge you to go to JuliaCon and register, by the way. So juliacon.org is happening. It's completely free and online this year. And please do register and check out the talks there. So that will answer many of your questions.
Yeah, so we have another question. What can we do with Julia like other than ML and scientific computing?
So
Uh,
Julia is a Turing complete language. You can actually do anything in Julia. You can write a web server, you can write a database, you can make a game, everything. The machine learning and scientific computing parts of Julia are its strongest suite, but you can pretty much do anything in Julia, and people already do all these things.
we have a one mindset question as well. Ashwin is asking like, what was your mindset while you were developing Julia?
That's a little bit of an open-ended question. I guess my mindset was to build the best programming language, the fastest and easiest to use. Is sort of what I opened up with, right? That we were really tired of all the old systems, like that we were using because of the levels of performance being so poor. Before Julia, I had developed a project called Circuitscape, which is a conservation, it's an open source conservation ecology project. And it was really just frustrating to see the amount of effort it took to get high performance. And that is sort of, what led to the creation of Julia. And, when you're developing it, you don't think about your mindset, you just kind of write code, right? So that's how it goes.
Ankit is asking like, which language is better than Jupyter Lab?
I think I would recommend going to JuliaCon and seeing the Pluto talk that Fons gave last year at JuliaCon 2020, and that will address the question. It's not whether Pluto is better than Jupyter Lab again. So I would strongly urge everyone to move away from the thinking of something is better than the other, something has to beat something else. It's what is different about it, right? What was the challenge with Jupyter, and why does Pluto even have to exist, right? And the main thing is that Jupyter is a language agnostic system, and so you get the same experience across a different set of languages, whereas Pluto is actually deeply integrated with the Julia language, and as a result of that, it can do a lot more magic in the notebook than you can in a language agnostic notebook. But both are fantastic projects. Oh yeah, and there's the demo that we had in there. So I don't think I understand this question. As a newcomer, would you first build your skills with Python or try and learn Julia right away? Um, it really depends. I mean, I have seen students in schools today who learn Julia as their first language. So I don't see any reason. I would say pick something that you are comfortable with, but there is no sort of natural progression here. Python does have a lot more materials online, a lot more books, and is often pre-installed on most computers nowadays. So it may be easier to get started with Python, but Julia increasingly is equally easy to install, has a lot of amazing materials out there, and will give you high performance. So I would say, if it were me, and this is a biased answer, I would learn Julia today, because if you learn Python, you're going to learn everything, and then you're going to learn the parts of it that are not fast, and then you have to learn something like Julia or C++ anyways. So might as well sort of skip that and go to the new thing. But hey, I'm biased, so.
We have a question from Divyang. Does Julia have the basic data analysis packages ready here in 2021?
So Dhairya will be covering some of this in his part of the talk. So just stay tuned.
Yeah.
But the answer is yes.
So
All right. So I think this was. It seems like people have a lot of questions, and I think they will really enjoy, hands-on machine learning. But I have to sort of take off right now. But thank you all for inviting me, and I hope you have a great hackathon. And hope to see some of you maybe even get motivated to contribute to Julia itself.
thank you so
Thanks,
much, sir.
Viral sir. Your presence had made a great contribution to our fest. Now onward, Dhairya sir will continue the webinar. He will talk about machine learning and machine learning libraries in Julia. Sure.
All right. Can everyone hear me fine?
Yeah,
Cool. So let me start with setting the state just a little bit. So I want to start with where Viral basically spoke about the importance of Julia, and he gave a really fascinating insight into what the mindset was, right? Like how something of a scale of Julia comes about. So the idea is that you have a lot of specialists, right, who develop very complicated, very advanced algorithms for solving a multitude of problems, right? And as Viral pointed out, that typically software is written twice, one in a higher level language and once in a low level language. And basically squeezing and compressing that cycle is something that Julia really excelled at. Now, another thing that Julia then did, right, which is this. Julia has also spawned a very healthy ecosystem of packages. And one really clever part of the language is that, most of the packages, I would say the vast majority of packages are written in pure Julia all the way down. What that basically means is that you don't have the second language to go to in order to get the speed. You have the speed available to you already. It also means that most of these packages written in high level language, you can actually go into the source code and hack around them, right? You can actually play with them. What it also means is that we have a very a very strong basis on which to develop our tooling around. So whenever we build new tooling, we only have to worry about what the language offers, not something that you can take for granted, and we'll see that later. So as we were looking at earlier, Julia can target a multitude of accelerators, especially important for things like machine learning. Now, I'm sure folks have seen a little bit of growth of how machine learning has come about. And as a question asked earlier was, apart from doing scientific computing, what else can I do with Julia? And the answer to that, as Viral actually rightly mentioned, is that it's a general purpose language, and you can basically build whatever. And Pluto is a great example of that. But it also means that we, for the computationally expensive tasks, we do want access to these GPUs and TPUs and things of that nature, so that we can actually solve the big problems that face our world today. So this is a comparison of the Julia GPU stack, which is again completely Julia all the way down, and we can see it work favorably actually compared to CUDA C, which is basically how every other CUDA library is built, right? So if you go to like a TensorFlow or a PyTorch, you would find a lot of CUDA C in there for the C parts of the language, which is basically where all the implementation takes place today. And the question basically comes, why do we need a language for AI, right? And you would notice some people that I've quoted here on the left. So Jan LeCun, Andrei Karpathy, Chris Latner, these are stalwarts in this industry, right? And what they have, pointed out is that deep learning essentially has kind of lived out its usefulness because earlier we did not know how to, leverage these neural networks as they're called, but then we later understood that we can add more layers and build these giant machine learning models, and then it's slowly but steadily coming to a point where adding layers is no longer the sensible thing to do anymore, right? Even though you have very large models, what actually needs to happen is that we have to find better ways to encode our model into something that can solve these tasks much more efficiently. Andrei Karpathy basically gave out a very simple definition of what software 2.0 looks like, and basically it goes along the lines of rather than writing the algorithms themselves, we basically think of the code as the model itself, right? The code has to define its constraints, it has to define the problem that it's trying to solve, and then we have to take learning from there and generate the actual programs that are needed to solve the specific problems. Um, Similar things have been said about Julia by some really important members of the machine learning fraternity. So, for example, Jeff Dean, who's the head of Google AI, and we saw, we showed basically how Julia can be used on TPUs as well. Now, machine learning happens on all sorts of accelerators, and it's important that we can target them efficiently, right? And Julia is built with this, notion that we do not want to add black boxes wherever we can avoid them. And this philosophy has basically meant that we target all sorts of things, be that smaller microcontrollers all the way down up to very advanced TPUs and GPUs that are coming out to them. So the idea essentially boils down to a very simple problem statement, which is that these models, these machine learning models, are really just programs. These are programs that you and I write as any kind of code base that we would. And machine learning problems are basically language problems because we need the language to be expressible enough, and we need it to be computationally efficient enough to actually work around these tasks and allow us to play with our problems in a manner that don't really restrict us given the tools that we have. And machine learning is one of those beasts which is famous for needing all sorts of compute that it can get. So be they the enormous data sets that we need all the time, be that we need to be able to do computation on distributed resources, on novel hardware, and deploy it on nearly just about anything from a microcontroller to a phone to very large cloud-based systems. But the problem that all of these frameworks actually put in place is that we always have to have this lower level language to get any performance out of. And these languages are not typically very expressible. Whereas Julia tries to flip that over its head. So you would notice that a PyTorch or a TensorFlow is largely written in a lower level language at the end of the day, whereas Flux is written in Julia all the way down. But we'll see how it can still perform at par, if not better, than any of these. So, what is differentiable programming, right? So let me do a quick and easy dive. So we want Julia because it's easy to use, it's fast, it's scalable, all of that stuff. That's brilliant. But deep learning typically requires brute force. And by brute force, I mean that we need the computational resources and as many of them as we can have. But we also need it to be ergonomic because these are typically very complicated tasks that we're dealing with, right? So we want a language that is expressible to be able to define these models easily. And at the same time, we need the performance. Scientific models are usually written in a low level language because of the performance reasons. But we want the best of both worlds. In Julia, the developers are sort of known to be very greedy, right? We like to have our cakes and eat them too, so to speak. So, folks who are, generally aware of how a bunch of machine learning works would probably be, aware of typical, object detection type models that, machine learning is known to solve all the time, right? So, if you have this thing called a convolutional neural network, its job essentially is to look take an image as an input and try to predict what objects there are and where they are and so on. So that's a very typical workflow, right? Now let's dive a little bit deeper into it and see what it's actually trying to do. So a convolutional neural network, typically what it tries to do is it takes a chunk of an image and then it will analyze the different pixels around it. The pixels basically become the features it's interested in, and then it will try to figure out the relationship of one pixel with respect to the neighbors around it, right? And that's essentially how a convolutional model works, on a very high level. And what the underlying principle of that is that it's trying to encode structure. So we're trying to find these structures within our data sets to be able to make, you know, interesting and intelligent predictions about our, data set and what it's actually trying to show to us. Now, let me say let's take this to the next level, right? And by that I mean we want our code to act as the model itself, and for that we we enter Flux and Zygote. So Flux and Zygote are this new take on what machine learning is going to look like. So we believe that there's going to be an entire section of users who are going to need the kinds of modeling approaches that we have typically seen with deep learning. So we will see models get bigger and bigger and deeper and deeper. But at the same time, we'll need significantly more newer approaches to how model building happens and the problems that it will be applied to, so that you can actually solve forward-looking problems. So encoding structure into our code bases is essentially where we take our cue from in differentiable programming. And Zygote is our vision into how this thing will actually take forward. Um, so one thing to note is that Zygote is how we've been doing things now, but soon, and by soon I mean, as Viral mentioned, with the release of 1.6, we're also releasing, our new age automatic differentiation engine called Diffractor, which will probably, also include a bunch of work that Zygote has done and take it to the next level as well. So, I mentioned earlier what happens if we want to push the boundaries of encoding the structure. And here I have a very simple simulation. So, this is a trebuchet model, and its job is to basically take this little stone thing and hit this target. Um, on the right, I have the code that actually runs this simulation. Okay. Now, typically you would, think of the different parameters that we can tweak. So be that the weight, be that the, air resistance, the air speed, all of that stuff is going to be accounted for while, you do the simulation. Now, it's important to mention that doing the simulation itself is kind of expensive. And if you want to take a very traditional neural network approach, we typically have to, generate a large number of simulation data for us to actually train on. Now, that is one way to do it. But if you look at the right, there is no neural network involved, right? What we've basically done is written the code to generate the simulation for us. And that's something that you would notice has been done by many, many, people in the Julia ecosystem and beyond who, take who are domain experts, right? And who are writing this code and um, that they're making it available to do the simulations. But if you want to add learning to it, if you want to use deep learning type approaches on it or differentiable programming approaches on it, we typically have to write an entire different section of code that can actually generate these feature vectors and train. But uh, on the right, as I mentioned, we do not have any neural network involved at all. However, if we were to apply things like Zygote on top of it, we'll be able to see that we can differentiate through the entire thing and we can train our models much, much more efficiently, as we'll see. So first thing is, okay, that's a great demo, but why should I care? And the question of why you should care is because this is just one example of how it's changing the world, and it's changing the world in today's time, right? And let me give you a very simple another example, and this might be something that people who are used to doing machine learning would have seen earlier as well. So this is the cartpole example, very famous example. It has this little platform and a stick. You can move the platform left and right. The objective is to keep the stick straight. And typically that means that you have a simulation engine, so you can have like a gym environment or whatever, where you can do all of these different reaction steps. Um, Now that's well and good. And the typical approach to that, solving this kind of problem, is called reinforcement learning. And for that, you have a number of fairly advanced algorithms available to you, and that's how it's solved. So you'll try to train a reinforcement learning algorithm, be it a PPO, TRPO, etc., on top of these things to actually make it do anything. And this is a fairly typical problem that people want to solve. It can be thought of as analogous to the kinds of problems that people want to solve today in a large way and tomorrow in the future looking fashion, right? Now, of course, this is how the model would look like using, if you were to train it using differentiable programming. And the idea is that we want to take whatever equations that we wrote to actually get our our simulations up, right, and use that to differentiate our models directly. That way, we're encoding a significantly more amount of structure into our problems, right, into our models. So the effect of that is that a reinforcement learning, model typically takes about 400 episodes to solve the cartpole problem, and the differentiable programming system takes only six. And that's because our updates are very, very clearly, guided by the kinds of structure that the program itself is imposing, the kinds of constraints that we have to take into control in, in the physical world. So it means that not only is it a lot faster, it actually produces better results, compared to reinforcement learning examples. So one other question is that, all of this sounds like it's kind of in the future, right? It's not today, but that's not true. And we'll see the practical side of differentiable programming take its shape right now. And the fact is that we'll talk about this later in the talk, that there are a lot of companies and projects using differentiable programming techniques to solve problems today. And let's just talk about the practical side of differentiable programming, right? So whenever we have worked with a very typical ML framework, we think of these loss functions, and the loss function is basically what you use to optimize a model to solve a particular problem, right? So this can be whatever kinds of loss functions. And for the most part, what happens is that our loss functions are basically given to us via the frameworks. But more often than not, we always have the need to write our own to solve the specific problems that we're out to solve. And it can be for many, many reasons. Either our problems are too novel, they're too specific, you know, we're trying to learn. So pedagogical examples are a great example. And for all of these frameworks, we typically have a lot of, you know, sort of there's this whole learning curve involved to write our own custom loss functions. But custom loss functions are a very important aspect to a machine learning or a deep learning world. But with Flux, we take a slightly different approach. We want custom everything, and the reason for that is, as I said, models are nothing more than just the code that people are writing, right? So there is no real notion of what a layer is. There is no real notion of what optimizing a layer is. It's just parameters that we want to tweak until we get them just right. So let me show you the practical side of what it means, right? So this is the same thing that I've defined in two frameworks. One of them is PyTorch and another is Julia. Now notice I said Julia and not Flux. And the reason for that is thus, right? If you look into the first one, you'll see this little torch.mean. So that means that we're using predefined and these black box versions of what is typically something a very well understood thing, right? We know what taking the mean of an array is, for example. And that means that, we are limited to the kinds of tools our frameworks provide to us. Whereas in the Julia side, our approach is a language wide approach. So we don't want people to worry too much about where their code is coming from. So that means that you know we use the same functions that the language provides by itself. So the mean is coming directly from Julia, and every other operation, the power operation, the subtraction, everything is typical Julia. But that doesn't seem too bad, right? Like we can deal with writing torch.mean. That's not too bad. Let me show you a slightly more, specific example. So the linear layer, uh, this is coming directly from PyTorch. You can go around, canoodling around their source code right now, and this is what you'll find. So the linear layer is a very, fundamental layer in machine learning, and yeah, it seems like there's a lot happening here, right? So there's this parameters thing, there's this tensor thing, Something about JIT is scripting. We're handling torch functions apparently. There's add what's a matmul, right? So there's a lot happening there. And we know from the maths of what a linear layer is doing, it's basically doing W, which is the weight, times the input matrix, which is X, W times X, plus the bias. So we know this is what that layer is doing ultimately. And we can see that somehow, right? We can see that it's doing matrix addition. We're seeing that it's doing a matmul, it's doing the bias add. So it is doing it. It's just doing it in a much more verbose manner. Whereas in Julia, this is what we do. This is the entire definition of what a linear layer that we saw in PyTorch would look like. And that significantly reduces the amount of complexity of our code bases. It means that we don't have to write as much code to begin with, and it means that we're not losing out on performance, right? Because we spoke earlier about why Julia actually is very focused on being a fast performant language, right? So that's a stock difference, right? That's this difference, you can't ignore that easily. And this is sort of where differentiable programming shines, right? Because we don't really have to worry about having special constructs for every single kernel that we're interested in. And we can just write code as we would normally and let our tooling take care of the learning for us. So this is how we would if we scale this whole system up. So we saw how it works with just a linear layer, but we want to be able to solve significantly more complicated problems. And the scientific world has a lot of very, very smart people working on very, very smart algorithms to solve very, very difficult problems. So this is a simulation of the Lotka Volterra system. So this is basically a predator and prey model, basically trying to model, the populations of predators and their prey in using some, ordinary differential equations. So the trick here is that this is a very computationally expensive task. But with the advent of scientific machine learning, what it means is that we're able to use our automatic differentiation tooling and inject neural networks where it makes sense to be approximators, and then train that whole system up as one. So again, we're trying to encode as much structure into our problems as we can, right? And the result of that is that we end up with some of the fastest convergence in these kinds of problems than we'd seen ever before. But that is not to say that Flux does not work with, typical deep learning, kinds of use cases. We obviously do. So here you see a small snippet of code which is doing this exact, wx plus b again. But as you can see that this involves near to no, work from the developer's side, right? We're just writing our programs as they make sense to us, and then we use the gradient call to actually get the gradients for our parameters that we care for. Um, so this means that our tooling makes life easier. You obviously have all the layers that you would expect from a TensorFlow or a PyTorch, so that we can work with those environments just as well. And the result of it is that today we have some of the fastest of these large networks. So be that a very big transformer or one of the classic resonets, all of that stuff is ready and available to you from the moment you start. But it's fast to boot, so you can not only hack around with it, it's easy to write, but it's fast to boot. And that basically means that we've garnered something of an ecosystem, right? It means that there's a bunch of people who've come around to actually develop so many more of these things. So for example, you have geometric flux there that does graph neural networks. You have scientific SciML for scientific machine learning, fast AI for very high level, very regular training routines. You have things like flux 3D, which work on 3D data structures especially well. So that's taking advantage of or differentiable programming uh, technology as well. and so on and so forth. So we spoke about SciML, and let me touch base on it a little bit more in depth, right? Because this is pretty important. Now, scientific programs usually required a lot of very smart people to write very smart code, obviously, but it also meant that they had to hard code a bunch of stuff, right? They had to hard code their adjoints, and that made life a lot difficult whenever they had to embrace a new technology. They had to write everything which was written in a manner compatible with uh, you know tools outside, or maybe not even then. But with Julia, we sort of flip the script again. We say, every code base is going to be capable of differentiation by default. So it means that we're able to, garner something of a, reputation for having tools that play well with each other. Um, so early work needed fast differential equations. That was a big problem. Then you needed to know what kinds of data sets you would have, and now you're going into encoding domain knowledge and using data driven machine learning algorithms to actually train your models on. So that's kind of the trajectory that it's gone. And the early work suggests that we're off to a pretty good start. So for example, the differential equations.jl package is basically a leader in the performance of nearly every you know kinds of differential equations that a lot of people have been working with. So as you can see, with parallelism, with the expressibility of the language, you're able to get numbers which dwarf the examples that are available in other frameworks. So for example, as you can see, it's 50 times faster than SciPy, 50 times faster than MATLAB, and 100 times faster than R's Dsolve at least. So that shows where we are starting at, right? And then because we're able to also have things like Flux play nicely with it, we get universal differential equations essentially, which is to say that you know any kinds of differential equations that you can write, and you can add things like neural networks in just the right places. You can basically start getting differential equations which have neural networks embedded within them. So a couple years ago, the idea of a neural ODE was touted as being a complete disruption in how scientific programs should be written from now on. And the interesting part of that was that the team that was working on it basically had to write. Um, they were able to make only like ordinary differential equations work with it, right? But the fact was that this mathematics was applicable to many other kinds of differential equations. But because of the composability of Julia, what we were able to achieve was that basically any kinds of differential equations, not just ordinary differential equations, could now take advantage of neural networks. And then lo and behold, we have this concept of universal neural ordinary differential equations. Um, and that was very much a disruption as well. As I promised to you earlier, I wanted to show you that we are making real world change today. And this example is coming out of Pumas AI, which is a very modern company that is working towards doing personalized drug discovery or drug dosing. And they show performance which is going to be 100 times faster than some of the modeling tools out there today. For that, they won a bunch of really prestigious awards. So this is the International Society of Pharmacology that awarded them the Special Interest Group poster, which was something something that takes a lot of work, right? So you have companies taking even more advantage of these things today. So you have Pfizer seeing 175 times acceleration compared to their existing models, which basically speeds up the process of the kinds of work that they are pushing by a significant amount, right? And this kind of software development shows the real power of differentiable programming. And not just that, there's folks using differentiable programming techniques in all sorts of things. So we saw, you know, graph neural networks become a very big chunk of how machine learning is going to look in the future. And of course, because we have the tools ready already, we have world-class graph libraries available at our doorstep in Julia. So using that, we're also working towards, you know, closed loop optimization of materials for battery powered aircraft. And it's not just aircraft, right? It's a number of different aspects that go into designing a battery, be that its life, be that its recharge cycle, things of that nature, and its degradation. All of that stuff is now taking advantage of differentiable programming to produce the next generation of batteries. So that's again very, very something that's something we have to look forward to. Not just that, as Viral mentioned, that you know every climate code out there in some way or form is taking advantage of things that are written in Julia today. And the climate project out of a bunch of different universities, but University of California being one of them, is bringing out the Climate project, and they are also making use of differentiable programming techniques to actually automate the process of finding out different weather patterns in the world, and so on and so on, right? So this is kind of where the future of machine learning is going. So you're trying to encode as much information and as much structure of the problem within your models, and you're using that to optimize for the right reasons, right? And then you're accelerating that whole pipeline by a significant amount. So it's not just that the programs that you've written individually that are faster, it's that the actual result of the composability is that you're able to solve a lot more problems, a lot more interesting problems today, as opposed to having to think about how you would do them in the future. Um, so all of these things together. So here you can see that performance boosts over Dimola, which is again a very industry specific piece of tech. We can show that the differential programming approach goes anywhere between 60 and 570 times faster. Um, all of that is to basically say that we have this entire platform for differentiable programming that actually pushes the envelope, so to speak, so that we can actually see differentiable programming techniques be used today to solve problems that are facing the world as we speak. So that's something of pride to a lot of the people who have built these tools. Of course, that means that we also, as I said, take care of the more traditional source. So Jonathan Laurent wrote AlphaZero, which comes out of the Google, the folks at Google, and this is a very simple implementation of what AlphaZero looks like compared to what they had written. But because we're able to scale it, with cloud resources and so on, we're able to see significant speed ups. Um, but yeah, so this is all happening on Julia Hub. You can check out Julia Hub if you like, and for a slightly different, you know, just an introduction to what we're doing. So you can check out the Flux, uh, website as well to get started. There's a bunch of examples, the ecosystem, all of that, the docs and so on. Um, yeah, feel free to reach out, and there's a bunch of things that the folks at Julia Computing we do to make it possible for people who are using Julia in the real world to make it even more productive for them. Um, Yeah, so that's what I had for now. Um, I'm happy to take up any questions that come.
Thanks, sir, to tell us more about the cutting edge technology of Julia. Now we will start our QA session.
Go ahead,
There is
Alex.
a question from Lokchat Malhotra. For an average computer, how big is data set when the difference in speed between Python and Julia start getting actually impactful to the work case?
So that's very interesting. That's an interesting question for two reasons. One is that, for very deep learning oriented tasks, you'll notice that you have enough data. But for cases where you just don't have data, then you need data efficient methodologies. And to do that, to engineer that in a Python is significantly harder, right? Whereas for, if you want to deal with big data sets, Viral, I think, already showed you some of the benchmarks where you can, load data just that much faster than Python. So, you see real world differences regardless of the data set, right? So it scales up and down in that regard. But when you have, a bunch of problems where the size of the data set is going to be limited, right, is when you want to look to these techniques as well. So this is just one of those places where it shines, apart from, just performance at the larger scale.
Cabell is asking like advantage of Julia over Python. Why someone should use Python, yeah, Julia over Python, even it's like they know C or C++.
Uh, okay, so this question is basically trying to ask, why should one use Julia if one already knows how to use Python? And the answer to that is, as Viral said, the world is big. Julia and Python will grow together, and you should basically be using the tools that solve your problem the best, right? And when you start to see issues with Python, for example, when the interpreted nature of Python starts to become a bottleneck, or when you have to delve into a lower level language to get the performance, you see that your productivity kind of starts slowly gets eroding, because you don't necessarily have to do all of that work and put in all of that effort if you have a way to actually get the best of both worlds in one package, right? So in that case, Julia becomes a very easy and natural option, right? As I showed to you earlier, writing a linear layer in a PyTorch versus a Julia, there's a world of difference. And the fact is that in Flux, that is how we define our linear layers, right? It means that it's significantly simpler to read than a PyTorch, and it offers the same performance, if not more.
Again, Cabell is
Uh,
asking, is Julia platform independent or dependent?
so you can find binaries for Julia on all your favorite, OSs. So yep, where you can model
Yes,
training. Yes.
I guess we have TensorBoard logger.jl library for monitor the model training and battery stops. Right
Yep.
now,
So you can use. There's a bunch of libraries out there. So TensorBoard logger is one. There's basic loggers already in all over the place. So like for people who do not want to use TensorFlow or TensorBoard, there are alternatives available as well. So yeah.
Shivanjan Basu is
yes.
asking how someone can join Julia community, not just as a user but also as a contributor.
So as we spoke about earlier, there are a lot of people who are contributing to packages, right? So one simple way is to start using Julia, start to understand the philosophy, and then delve into the packages, look into what the packages are doing, try to send contributions their way, or start your own packages if you feel that there is a void or something that you want to do special. So yeah, there's many ways, and there's GSOC as well. So many platforms, including Flux, do accept Google Summer of Code as well as Julia Summer of Code students for working on various domain problems. So that's another key way of contributing to the language.
Sir, as you are
Uh,
also a mentor in Google Summer of Code, can you tell us more about yeah, under the umbrella organization of Julia, what are the several libraries or components where students can can apply for Google Summer of Code under Julia?
Sure. So the simple answer to that is go to julialang.org and you have the JSOC tab right there, right? So let me share my screen again. Right. So if you go into julialang.org, you'll have the JSOC tab right here, and here you can find the various, grants and programs that Julia language does take part in. So you can head over to the projects page, and you can see that there's a bunch of different, you know, domains that we accept students for. So you can go into the thing that interests you, be that machine learning, be that working with graphs and graphics, uh, whatever. And for more, Flux related ones, you can head over to the Flux GSOC page as well. And many of these organizations basically put all of their projects in like a singular place for people to find.
Okay, thanks. Sir. There is one question regarding how Julia is planning to make a space in the field of ML, where most of people are still using Python libraries.
So that's really interesting. Okay. The first is that there are a lot of people who are using Julia in the machine learning space already. Um, be that for actual deployment purposes or research. There's a very healthy number of people who are using Julia today as we speak. Um, as far as how do we plan on making our space, as we mentioned earlier through the talk, with how this whole industry of machine learning is progressing, we see the need for scientific modeling to also take part in this, and doing that in most other languages, for example Python, is one of those bottlenecks that people are facing all the time. And that's when they also start noticing these future looking problems being solved by a modern language like Julia.
Uh, the question by Suvanjan Basu is more concentrated on CUDA code. Like, what is the difference between the general code in Julia and the CUDA code of Julia? Like, there
So
is some different syntax or something.
So I'm sure people who have already worked with CUDA would be used to thinking like you have to program for CUDA completely independently for it to work, right? Whereas that's not the case in Julia. The same program that you write for CPUs more or less would work for GPUs as well, and it can do it efficiently because of multiple dispatch. What we're able to do is we're able to dispatch on the right kernels based on the different array types that we deal with. So for example, if you give it a CUDA array, Julia will automatically compile functions which can work on the GPUs. So CUDA.jl is a project which does exactly that. So it provides these array types and then compiles it to work on CUDA-enabled devices. So that way, the code that you write once is good for both CPUs and GPUs. However, for very specialized tasks, so for example, if I want to use, cuDNN, which is another very famous, project which is specifically made for machine learning, then for those cases, we also want to nudge Flux to use those kernels as well. But that again, that's not to say that you can't, just use the normal ones. It just means that you also have the option of calling into those libraries.
Okay. This question from Risika Raj. Does Zygote provides an extremely low overhead add-app interface?
That's very interesting, and yes, that is true. So while all or most other AD frameworks that I'm aware of, especially PyTorch and TensorFlow, for example, what they have to do is they have to, have this overhead for calling into their AD, and that's mainly because you have to do a bunch of things eagerly. Whereas with Julia, we have to when we compile down our systems, we're also able to compile down the backwards pass at one go. So what we end up with is through Zygote, what we end up is with is uh, an AD which has next to no overhead. Actually, I think it's about like 1,000 times faster than AutoGrad, something like that.
That's great. Rishika is again asking, does ML-based reinforcement learning has advantage over model agnostic methods?
So, yes and no. It depends on the tasks that you're dealing with entirely. But what we have seen from our experiences working with differentiable programming, we've noticed that it, we can beat either of them using the structure of the simulations to begin with. So, for example, we tried to train basically what amounts to a self-driving car using just the image of what the car would see and the controls and how it would respond. So that's with just that information, that simulation engine that we generated, we were able to outperform a bunch of these model agnostic tasks as well.
This is one question from Indrani. How code from other languages are being run on Julia, like TensorFlow? Yeah, you are talking about TensorFlow and scikit-learn packages on Julia. Then how it is running?
So that's a very interesting question, and it has a little bit of history behind it. So Julia is a new language, right? And the fact is that for any new language, you wouldn't have many high performance libraries from the get go, and you wouldn't have the high performance libraries if your language can't do the stuff that people want to do with it, right? So it's a bit of a chicken and egg problem. So because of that, Julia very early on developed a very strong interoperability engine. So basically, if you want to call into C, if you want to call into Java, things like that, you can do that very efficiently. So also Python, for example, so we have the C call, which works directly with C libraries. You have PyCall, which can call into Python, and Java call, which can call into Java, so on. Um, Interestingly, since things like TensorFlow and scikit-learn internally work on C and C++, we're able to target those APIs directly, which means that we can basically bypass all the Python in there entirely. What that also means is that the Julia version of TensorFlow tends to perform a little bit better than the Python version because you don't have Python's overhead. Um, but yeah, that's how it works. We have a very strong interoperability environment baked right into the ecosystem. So using that, we're able to call into all these things.
It is one question about like how we can use Julia, yeah, Julia in CUDA. Like people like Python has Colab or they have Kaggle kernels and also have images on Google Cloud and AWS. But if we don't find the images of Julia CUDA,
So the thing with Kaggle is it's basically promoting GCP right now. So sure, but if you want to go to Colab, you can definitely just download Julia and start using Julia there and then. That's something that you can find on the discourse. So Julia has a discourse, and you can find how to run Julia on Colab. Uh, so that's something that you can do. And for the most part, I think there are certain images available. And if not, what you can do is you can jump onto this platform called Julia Hub. So juliahub.com. And here, what you can do is you can actually run your code, you know, on cloud resources directly and on demand. One other thing that you can do, oops, let me not do that. Yep. One other thing that you can do is you can, download the Julia Hub extension to an IDE that you like, so be that Atom or VS Code, whatever. You can, download Julia on it and yeah, call into the cloud resources directly from your IDE with single clicks. So let me
okay,
let me show that really quickly.
yeah, sure.
Right. So if I open my IDE, this is where Julia Hub, the interface basically opens. It'll connect to, the servers and everything. You can choose the kinds of models you want to run on CPUs, GPUs, whatever, and basically click Start Job. That's basically it. That's as easy as you can want it, right? So this is an example of Alpha Zero, which can also, work as I mentioned earlier. So you have your code right here. You have Julia Hub working right here. And once it basically connects, all you really have to do is um, click Start Job and bippity boppity boo, we are good. Right, cool.
Yeah.
Do we have other questions coming in?
Yeah. Yeah. There are any more questions?
Last question, sir, from Hers. Can I use Julia instead of Wolfram Alpha or R software?
Of course, I mean, Wolfram and our studio are, props to them, kudos to them. They've done a lot of work in their, domains, both known for working on data science, but the fact is that you can, just hook into MLJ and in Julia and get the same kinds of capabilities. You have splines and whatever that you need from both from Alpha available, as pure Julia code, uh, just implementations in pure Julia. So yeah, definitely cool. So that was a lot of fun. Thanks
Yeah.
for inviting.
Thanks, sir, for joining us on in this event. Like it was a quite good event, and we get lot of things to learn.
Yeah, no, definitely. Happy to take on any other questions you guys might have. Please visit, fluxml.ai, go to the GitHub. Feel free to, try to play with our tooling, start the repos. That helps us a lot. But other than that, yeah, that was brilliant. Um, Thanks for inviting us over, and hope you guys have a really good hackathon.
Thank you, sir.
Yeah, thank you so much, sir. Bye bye. Take care.
Bye.
All the best.
Thank you, sir.